Okay, we changed topic again today. First of two gear lectures. If you've had ME 3310, this will be a review of what you learned there, because the first of these two lectures is about gear kinematics, and the second is about stress. So we have something called the fundamental law of gearing, which says that the angular velocity ratio between the gears in the gear set must remain constant. By gear set is meant a pair of gears, and there are two flavors, as shown toothless there, either internal or external. External gear sets turn in opposite directions, that is, the gears do one to the other, and the internal sets members turn in the same direction. So that means that their gear ratio, which is the m sub v velocity ratio that you see in the upper right, which is defined as the output speed over the input speed, omega out over omega in, would be minus for an external set and positive for a internal set. And you can also express it as the ratio of the radii or the diameters, or as we'll see in a bit, numbers of teeth as well. And as you know, the purpose of a gear set is to trade speed for torque or vice versa, the product of those two things being a constant for a given amount of power in the system, because torque times speed is power. So if I increase the speed, I have to reduce the torque and vice versa. So the most common application for gear sets is to reduce speed and increase torque, as in the transmission in your automobile, where you want to be able to get a lot more torque to start the car moving, put it in a gear ratio that has an increase in torque, and you trade off the speed. So the mechanical advantage of the system, the MA in the lower right-hand corner, is the inverse, the reciprocal of the velocity ratio, because of that inverse relationship. I trade one off against the other. So the mechanical advantage is 1 over mv, or another way of putting it is omega in over omega out, or r out over r in. Okay, that makes sense? So as I said, we can also express the ratio of the velocities in terms of numbers of teeth. Since they have to be the same size teeth to mesh together, then I will have a ratio equal to the ratio of the radii, whatever the tooth size might be. And this shows what's called a simple gear train, which is defined by each gear in the train. Now, the train is more than two, is on a separate axle or shaft. And each of the sets, if I go from 2 down to the bottom, say 2 is my input, so the first ratio will be 2 to 3, in over out, and then 3 over 4, and then 4 over 5, 5 over 6. They're all negative because they're external sets, and those signs, of course, are going to result in either a plus or a minus over here. But notice also that all the intermediate gears cancel one another out in that equation, and that ratio is only a function of the first and last gear in the set. So a simple train is not very useful. Its only value is if I use one additional gear, total of 3, to reverse direction. And that's how you achieve reverse in your automotive transmission, by introducing a second gear, in some cases, in standard transmissions. A more practical way to put these gears together is as a compound gear train, as you see here. And the definition of a compound train is I have some stuff in parallel, the other was all in series. And so at least 2 gears have to share the same shaft in a compound train. So here we see, let's call this the driver, the input shaft over here, which has a ratio, or rather a number of teeth n2. So that gives me an n2 over n3 with a minus sign for the first set. But of course n3 and n4 are not a real ratio, because it's 1, right? The speed is the same, I should say. So the omegas are the same. It's on the same piece of metal. So I don't put anything in for 3 over 4. But we have a 4 over 5 when you go from here to here. And when you multiply those, obviously nothing cancels, and I get the product of the two individual ratios. And you can compound it with additional stages, if you will. Each of those is called a stage of the gear train. And this would have same direction motion, because in effect this center pairs acting as an idler as well. I could package this differently such that the input shaft and the output shaft are collinear, which is a very handy thing from a packaging standpoint because the shaft appears to go right through the transmission and out the back side, but it doesn't in fact do that. It goes off to the side through this counter shaft and back. This is referred to as a reverted compound gear train, the reversion being the fact that I brought the output shaft back to the same line of centers as the input shaft. That introduces another constraint in terms of the numbers of teeth or the sizes of the gears that I can use in order to make that be true, so their center distances are the same. If I free up one of the pivots, back up a step, this picture over here shows the same gear train we were just looking at a moment ago, label 2 and 3, but I've put a physical shape to the ground link, arm 1 here, whereas on the previous drawings I didn't bother to draw the ground link, I just showed fixed pivots that would imply that there's a connection between them, since they're all part of the same ground plane. But if I represent that physically, and then I pull this pin away from the ground, that is, I take away this grounding pivot, then I'm able to rotate that assembly, namely the arm and link gear 3, around gear 2. And now I have 2 degrees of freedom. And so to make that behave, I either have to put in 2 inputs and get out 1 output, or take 2 outputs in the result of 1 input. And it's used both ways. These now take on names that are fairly obvious. We have a sun gear, a planet gear, and an arm, or sometimes called carrier. So the term arm and carrier mean the same thing. It's not as easy to calculate what the ratio of this train is. It's not so intuitive because the ratios between the gears only apply with respect to the arm as relative speeds versus the arm. And that's the same as it was over here, but the arm was fixed. So this gear ratio is with respect to the arm, but the arm wasn't able to move. Now that I am moving the arm, which is a second input, I can only do the calculations for gear ratios with respect to the arm, and that leads to this formula. On kinematics, I went through a whole long wheeze to show you how to solve these equations with a tabular method because it sort of showed you the steps of what was happening. I'm not bothering to show that here. There's also a straightforward equation method to do it, and it uses the so-called velocity difference equations. If you recall, have the form omega of b is equal to omega of a plus omega of b versus a. And here the B's and the A's are going to become the first and the last gears, or rather the first and the arm, the first gear in the arm in this case, and the last gear in the arm in that case. So this is the relative velocity of first versus arm, and that plus, vectorially plus, the omega of the arm gives me the absolute velocity of the first gear. Last gear is a similar expression, and the train ratio is simply the ratio of the last versus arm over first versus arm, which can be, from substitution, written in this fashion here. Last minus arm, final minus arm. One of those should be first. That's a typo. This should be first, not final. The last is the final. So that's a typo. So I can very quickly calculate the train ratio for this system. Now typically we have also a ring gear added to the system. It's difficult to get the motion off the planet gear because it's orbiting around the sun. So I can't get a hold of that shaft very easily. But by coupling the planet up to a ring gear and making everything nicely concentric, it's self-reverting, all comes back to the same center line. Now I have the arm on this pivot, and concentric with that I have the sun gear on a tube surrounding the arm, which itself is a tube surrounding some kind of shaft here, and the ring gear still again surrounds that. The arm is keeping the planet in mesh with the sun and the ring. So now I have, again, 2 degrees of freedom, so I can put 2 inputs in, one to the arm, let's say, and one to the ring, and take the output off the sun. Or I could put, one to the sun, one to the arm, take the output off the ring, or one to the ring and one to the arm, take the output off, et cetera, right? And typically in these situations, the second input to one of the other of those two things is 0. So if I lock, let's say, the sun to ground temporarily with a brake, then I will get a certain ratio. And I showed you in the kinematics class, if you took that with either me or Professor Van der Ven, you saw how we can get both forward and reverse motion out of this thing by locking different pieces, and how we can get quite a variety of ratios. And this is the principle on which the automatic transmission for automobiles and trucks is based. The gears are always in mesh. You don't have to shift them in and out of mesh. And I can have a variety of ratios, including reverse. Recall Ferguson's paradox, where I showed you how the same gearbox could go both directions simultaneously with enough sets of gears. So these are very, very useful devices. And you can buy planetary gearboxes off the shelf to put in front of a motor to reduce the speed to whatever you like. And they're quite handy. The fact that they're self-reverting is nice because you stick them on the end of the motor and the shaft just sticks out the other side of the gearbox. So it looks like the motor shaft, but it's traveling at a different speed. The gear teeth have a particular shape, and we talked about that at length in kinematics. I'm only going to briefly refer to it here. I described how the involute has some magic to it for the shape of a tooth. And there's another curve that's been historically used in clock making called the cycloid, which you should be familiar with from cam design, which is also useful for teeth. But the involute sort of took over from the cycloid a century or more ago because of one particular advantage it has over the other. The definition of an involute, which has a mathematical formula that I don't show you here, but geometrically I can construct it by taking a piece of string, wrapping it around a circle of some sort, which we're going to call the base circle, and then stretching the string taut, and then unwrapping it from that circle. And imagine I have a pencil tied to the end of the string, and it draws that red line that you see. And that has a particular shape called an involute. And the property that's of interest here is that every point on that red curve has a tangent. Has a normal that is tangent to the base circle. Say it correctly. So the normal to the tangent of the curve, I don't show the tangent of the curve, take this point right at the very end. The tangent to the curve, which I did not draw, would of course be perpendicular to this radius, right? That's the definition of tangent and radius. One is perpendicular to the other. And so that radius goes back to this base circle and is always tangent to it. So when we use these shapes for gear teeth, we get the nice property that the forces all travel down these strings and all end up coming to the same radius. And that's what gives me the constant ratio, despite the fact that the teeth are coming in and out of engagement. So I keep my ratio the same as if I were rolling two cylinders, one on the other with no slip. And the teeth are guaranteeing me no slip, and they're also not introducing any error into the ratio, as did the old-fashioned gear teeth that I described out at Sturbridge Village, where there are lumps of trees stuck into a big wooden disc to turn the saw in the mill and whatnot. And so you got a peg and a peg between two pegs, and it's rattling around with a lot of backlash and so forth. And it's perfectly fine for sawing wood, but if I want to try to drive my cam in time with my pistons, I don't think I want all that error in there. So I want to have a nice shaped tooth so that I keep a constant ratio and don't let things get out of phase. Okay? So that's the magic of the involute. So there's a picture of a tooth that is made with involutes on both sides. And here's a little sketch of the geometry, the kinematic geometry, as it appears at a point where the two teeth are touching, one driving the other. This guy, the pink one's driving the gray one in this picture. And we have a pitch radius for each of these guys, which, if different, would be your ratio. You know, radius of one over the radius of the other is the gear ratio. And that pitch radius is to the pitch circle, and the pitch circle is the theoretical cylinder that, if we could make it not slip, would do the same thing. If I could just run two cylinders together with no slippage in pure rolling, then I would get the same motion. But, of course, that's problematical. If I do slip, then things get out of time, so the teeth are there to guarantee the timing. This line in red, which becomes black at some point up here, I guess it gets onto the circle, That black dotted circle right there is the base circle. And the involute line, the string, so-called, as I called it earlier, runs from tangent to the base circle of this gear to the base circle of the other gear, and it goes through the pitch point, which is at the confluence of the two pitch radii. And so no matter where those teeth are in the mesh, those forces along that common normal, which is the transmission axis, go through the same point at the same radius on both gears. Radius may be different on each gear, but it's at the same point, and that gives me the constant ratio. That makes sense to everybody? Any questions on that? This just shows you the standard terminology, at least in the United States, for gear teeth, which are well standardized, but standardized for a century, if not longer. Circular pitch is defined as the circumference of the pitch circle divided by the number of teeth. So it's the arc length along the pitch circle from tooth to tooth. The diametral pitch is a function of diameter, but for some reason, I don't know whether they fell down and hit their head, but they made it upside down when they defined this many years ago. So instead of D over N, it's N over D. So the units are reciprocal inches. D is the pitch diameter, i.e. the diameter of that pitch circle. Now, it's very difficult to measure the circumference. Of course, I can calculate it once I have the D, but the pitch diameter is fairly easy to get your hands on, so this has become the standard to define tooth size. Now, in the metric system, they did it a little more sensibly, in my view. They turned it right side up, so it's D over N, and they call it the module, and that's measured in millimeters. This is reciprocal inches, this diametral pitch. It's 1 over inches. So you have to keep that in mind when you look at the numbers for diametral pitch. I'll show you a table of them in a minute for standard numbers. But it's inverse, so the bigger numbers are smaller teeth. A large number of diametral pitch means a small tooth and vice versa. So the other parameters you see mentioned here are face width. That's going to be of concern to you in design of the gear, because clearly if I add more length to it, I have more meat to resist the forces. So that's going to be a factor in our stress calculations. The shape is defined by the involute standard. The addendum, that which is added on, is from the pitch circle out to the tip. And the dedendum, that which is subtracted from, is down to the root. And the dedendum is a little bit bigger than the addendum, so there's clearance for the other tooth to go through without stubbing its toe. The base pitch is the diameter of the base circle. And of course, these circles, pitch and base, don't physically exist. I can't pick up a gear and see it painted on there. They're there, but I don't see them. So this is a set of specifications that is put together by the AGMA, which stands for the American Gear Manufacturers Association. A huge organization, and it's funded by the gear manufacturers. They pay substantial fees to it every year to be a member, and in return for that, they get the benefit of research that's done both by AGMA directly and by gear manufacturers that are supported by money goes back to the manufacturers to do testing, and then the information is published so that everyone's on the same level playing field. So that this promotes uniformity. It means that you can buy a gear of a certain specification from one manufacturer and expect it to run properly with one of their competitors' gears. So you don't have to always go back to the same company to get your replacement gears and so on. So it has worked out very well. The ball bearing industry does the same thing. They have a similar arrangement in a similar organization. So pressure angle, which I should have mentioned that when I had this picture up a couple ago. I don't show it here, but it's the angle between the direction of velocity at the pitch point, which of course is tangent to the circles, and the direction of push. The direction of push is always along the string, which we more properly call the common normal or the axis of transmission. So the industry has standardized in the U.S. on 20 or 25 degree pressure angles for coarse pitch and 20 degrees for fine pitch. And the addendums are defined as a function of the diametral pitch, which of course defines the tooth size. So it's just as high as its diametral pitch. It's a little bit deeper, and so forth and so on. So these are easy to compute based on the standard. Now, which pressure angle do you want to pick? Well, the original pressure angle that was standardized in the U.S. was 14.5 degrees, and you see that on the left. And those are still available because there are still old gears out there that break, and you've got to replace one with the same diametral pitch and the same pressure angle. So I can still buy those, but you don't find that many in the catalog because they've been more or less obsoleted. The 20 and the 25 are the ones that are recommended, and you'll note that the 20 is the only one you get with the smaller teeth. For larger teeth, they recommend the 25 in many cases, and the reason is quite obvious from this picture. If this is loaded at the pitch circle with a force, and of course there's two components of force. The force is actually coming down from the other gear like that, so there's going to be a tangential component and a radial component. The radial component is going to show up back at the pivot, the axle for the gear. And the tangential component is going to go into torque and make the thing move, right? Well, that tangential component, which is the larger of the two because of the small value of the angle, is going to be putting that tooth in bending, isn't it? And it's a cantilever beam, so we know that the worst case moment is down at the root here. And so that's where my stress is going to be maximal, and that's where it's going to break. So you can see the advantage of the larger pressure angles. Now, the larger pressure angle, of course, means I have a larger component toward the center. But I trade that off against more meat in the gear tooth, so I'm less likely to break with the same force or even more force tangentially. So that's the reason that the recommendation nowadays is to go toward the larger pressure angles. Here's where I show the pressure angle. This is a similar picture to what we saw before, but with more labels on it. This is figure 12.4 in your text. So this is referred to as the common tangent right here. What it's tangent to is the shapes of the involute teeth at the pitch point. And perpendicular to that is the common normal, also called the line of action, also called the axis of transmission, which label I didn't put on this one here. Pressure angle is, as I said before, between the direction of velocity and the direction of force, which is always along that line. And that's about all we need from this picture, I think. It shows some other labeling. I talked at length in kinematics about the issue of interference and the fact that if you have relatively large teeth on a relatively small diameter gear, then the geometry is such that the base circle, which is the imaginary circle from which the string is being unwrapped to generate the involute, is above or outside of the root of the tooth. And since I don't have any string below that, I don't have any involute below that either, so that's just made as a radial line, and then the involute exists from there out. When I made it with the other gear, which is presumably bigger, by the way, the terminology is standardized. The small guy is always the pinion, and the big guy is always the gear. Okay? So pinion is the smaller of the two. So I make that with a larger gear, and this I show the base circle is below the root, so therefore this entire tooth is an involute, and of course the tip would be anyway. So I have an involute gray tooth meeting up with a pink non-involute tooth, and there is an interference that results. And that material will never show up on the gear because the way I make the gear is to use a cutter that looks just like that tooth. And so when the cutter goes through there, it's going to take that material away, right? And in the process, it's going to narrow that tooth down right where I need the strength the most, right at the root of the cantilever beam. So this interference problem gives me a weaker tooth. So the rule of thumb is given that you should not have fewer than n teeth, and n varies based on different parameters, and those are all defined in a table here. So I don't want to have too few teeth on my pinion, otherwise I run into this interference problem. I weaken the teeth, and they're more likely to break. So here are some guidelines for minimum number of pinion teeth to avoid interference with a 20-degree full-depth pinion and full-depth gears of various sizes. So here's your minimum pinion teeth and a maximum gear teeth for that. So as the number of teeth on the gear come down, it also drives down the largest, the minimum number of pinion teeth allowed. And there's fairly small numbers of teeth, 13, 14, etc. Now, in more recent times, which is like the past 50 years or so, to solve this problem, the AGMA defined a new standard for gear tooth shape, and it's called profile shifted teeth. It's a very simple concept. Instead of making both gears have more or less symmetrical material above and below the pitch circle, I think 1 over PD up and 1 over 1.25 PD down or something like that, they profile shift them. So the smaller guy has his shape changed so that the involute can remain, here's the base circle in red here, so it in effect lowers the base circle closer to the center and gives me an involute shape outside of the fillet radius in the root. And so these are full involutes all over their surface, and I don't have the interference problem. And these are now standardized and available, so if you do need to have a very, very small pinion in order to get your package down, you want to go to the profile shifted teeth rather than the standard teeth. Now, another parameter that I didn't stress very much or even introduce in kinematics, because it only really applies to the strength of the gear teeth and how they run, I guess I did mention it, is this contact ratio defined as Z over the base pitch, P sub B. So depending upon the size of the teeth and the diameters of the gears, I will have some number of teeth on average in contact as it comes through the mesh. And the worst case, of course, is I have only one tooth in contact at a time. Then that one tooth's taken all the force of the mesh and thus is more highly stressed. I'd rather have the teeth share the load. And I can do that if I arrange the geometry of the teeth so that I have a better so-called contact ratio, which is the ratio, the average number of teeth in mesh at a time. And this parameter Z is called the length of action, and that is in essence the length of the arc over which the teeth are in full engagement until a given tooth makes engagement. If I'm driving with the pink one, it first touches the tip of the gray one right there, and whoops, it stays in contact until it leaves up here someplace. And so I can calculate that length of action from this rather messy formula, which involves pitch radius, RP, addendum of the, I should say pinion, that's the radius of the pinion, and the addendum of the pinion, and the pressure angle, and this is the radius of the gear, the addendum of the gear, and the pressure angle, which is the same for both, and some factor C, which has to be defined elsewhere. I didn't put that formula here. So it's just center distance between the two is your C, and cos phi. So I can calculate that for any given mesh. And I'd like the biggest contact ratio possible because I'm going to get better load sharing in the process. As you, I think, are beginning to appreciate, you can't make anything perfectly. There's always going to be some tolerance due to manufacturing errors and so forth, and assembly errors, so that even though I theoretically wish to have a certain center distance to make these two gears run properly together and have their contact point in the on the line of centers be right at the pitch circle, I may have some error in the center distance. Maybe the holes were drilled improperly. And that, in my example here, pulls the pinion out of the gear, and that affects my loading. It also affects the way it runs. But here's where the involute becomes really handy, because even though I pull that back, the only result in terms of the motion is I increase the pressure angle from its original 20 to 23 degrees, because my magic string is still theoretically tangent to both base circles. And my pitch point, while it's moved up on the tooth, nevertheless stays in the same place for all teeth in mesh. So I don't screw up the ratio. And that's the difference between the involute and the cycloid teeth. If I pull cycloid teeth apart, I will change my ratio. This does not suffer from that problem. Cycloid teeth are still used, I'm told, in timepieces. Whoever's making those today that don't have little crystals in them and digital digits. I happen to have one on my wrist that still has hands. But they're made very precisely, to very tight tolerance. So if you take care of the tolerances, you don't have to worry about the cycloid giving you an error. This shows the relative sizes. They're not an absolute scale of the various diametral pitches, rather. And again, small numbers are big teeth and vice versa. So they typically run from 4. They go to 1. This shows 4 as the largest. But here are the standard numbers of diametral pitch that you can buy from a gear manufacturer in the United States. The metrics will be totally different because they're reciprocal, they're in millimeters, and you can't run metric gears in mesh with US gears and vice versa. The principles are the same, but the standards are different. Here's some pictures of typical gear arrangements, and I've actually brought a bunch of these into class in kinematics. You may remember if you were in that class. Spur gears are defined as having teeth that are parallel to the axis, helical, as the name implies. The gears are actually pieces of helices, and they mesh differently. Helical gears can be run 90 degrees to one another. So these are the same type of gears, but one of them has been flipped 90 degrees. I think you have to have a right and a left hand to do this, to make that work. Bevel gears are made from rolling cones rather than rolling cylinders. And if we put teeth on them, we get bevel gears. And if the teeth are straight like a spur gear, it's a straight bevel. If they're helical like this guy, it's a spiral bevel. And another common configuration is a worm and worm gear. And this is really a special animal. This worm is like a thread. It in fact is a helical gear in which you've made the helix angle so big that the tooth goes round and round and never stops. Okay? And it's exactly analogous to a bolt, except the thread contours are different. They're much more rugged than a bolt would be. And you can see they're quite fancy. And that meshes with a gear that looks a little bit like a helical, but the tooth shape is very different. And these are actually made in matched pairs. And the contours of the teeth are not involutes in this case. They're a much more complicated three-dimensional curve. This has a couple of big advantages. One is I get a huge ratio because this worm has effectively one tooth. It's one continuous tooth wrapped around itself. And so if I have 20 teeth on the worm gear, I got a 20-to-1 box in a fairly small package. So, and I've got a big 20-to-1 reduction ratio then, right? And another advantage of these is they can be designed so you can't back drive them. Now, clearly, these guys are happy to go in either direction, right? So if I'm designing a jack for my car, I'm going to turn the crank. I don't need a lot of mechanical advantage to lift that heavy car, right? So I need a lot of ratio in there. If I use some spur gears, what happens when I let go of the handle? Down on my foot. So there I want a worm and wheel with the helix angle small enough that it can't drive backwards. If I make the helix angle bigger, then I may get to a point where the coefficient of friction is not sufficient to hold it, and it may run backwards. It's called a back-drivable worm. But I have to go to some trouble to make the worm back-drivable. Normally they would tend to be non-back-drivable. So for a situation where you need to lock something in place, it's ideal. They're somewhat expensive, as you can imagine, because of the complexity of their shapes and so on. And they also are very poorly efficient. This pair up here is about 98 to 99% efficient per set. This one's more like low 90s because there's some sliding going on at the teeth, more so than over here, so you've got more friction happening. This one would be even less, all the way down to 50% to 80 or thereabouts, because you've got a lot of sliding going on when they're crossed. These can be almost as good as these, maybe 90%-ish. These a little bit less. Here you're looking at 40 to 60, maybe 70 with some care. So you're going to lose more energy, more friction with the worm. Some more detail, and I think I've already said all of this stuff. One thing I didn't mention is I can shift these in and out of engagement to make a transmission fairly easily, because I can slide them on their shaft with a spline perhaps in the shaft, which is just another set of gear teeth, and slip them in and out of engagement. Backlash can be a big problem here because as the teeth come together, there's always some clearance, and they suddenly slap. If the torque reverses, they'll rattle around in the mesh. They're not expensive. They make a lot of noise. Helical gears run quieter. There's your efficiency numbers. They're obviously more expensive. They run quiet. They do now introduce an axial force component that I have to deal with in my design. So looking at the top pair, which are in parallel, they're going to try to spit themselves apart axially as well as radially, right? So I have to have some thrust bearings of some sort to keep them from moving, as well as the radial bearings. Yeah?
Are the hard transmissions helical gears? Is that correct?
That's correct. Most since World War II, they've been universally helical. Before World War II, they were Spur mostly.
So where's that efficiency loss coming into play? The slip?
You've got rubbing going on between the helical teeth to a greater degree than you have with the Spur teeth, that's all.
Okay.
They're wiping one another as they come through the mesh, whereas the Spur gears sort of push one another through the mesh. And they slap. That's why the Spur gears are noisy, because when the teeth pick up, it rings the gear and it will whine. If you have a standard shift car or have driven one, you may have noticed that when you go in reverse, you'll hear a whine. Spur gears in the reverse train, because you have to shift them in and out to get the reverse direction, right? You've got to put the gear in place. But the forward gears are all helical for quietness, and you don't hear them in the forward direction. You only hear them in reverse. Actually, some transmissions have helicals in reverse, too. I had one of those some years ago. It didn't whine going backwards, but it was harder to get into reverse. You had to muck with it. Had to put it in second first, and then to lock the thing up, and then quickly put it back in reverse to get the helicals to engage. So that was the trade-off. I'm not sure why they bothered, because do you care if you make noise backing up? How often do you back up, right? But that might make you wonder, how do you shift the ones in forward if you can't take them apart? And the answer is it has something called a synchromesh clutch that actually engages and disengages, and the gears are freewheeling on the shafts. I went through that in some detail in kinematics. Another advantage you get almost for nothing here, for the same number of teeth, same size gear, I get a stronger tooth, because just think about the geometry. If I have a certain diametral pitch, that's effectively defining the width of the teeth as I go around the circumference, right? And if that's the same for both the Spur and the helical, the fact that the helical's on an angle means I have a Pythagorean theorem issue, right? So I have a longer hypotenuse on the angle, and there's more meat in the direction of loading, because the loading is now normal to the helix. So I actually pick up a little bit of cross-section for the same size teeth, which of course is you trade off by making the thing smaller and lighter and less material and thus less expensive, and get back to the same strength, right? Harder to disengage, as I mentioned. Biggest disadvantage here is the axial thrust. If I'm passing 10,000 horsepower to a propeller of a destroyer, and I'm using helical gears because I don't want the enemy to hear me coming, which is a pretty good idea, I'm going to have one big axial thrust bearing in there that's going to be lossy. It's going to take away some of my power, right? So to avoid that problem in such an application, since I'm building destroyers, I got all the money in the world, right? I'm the Navy. So I build a herringbone gear, which is two helicals, right and left hand, put together in the same chunk of steel. And now I cancel the axial force within the gear. And I don't need the axial bearings and the associated friction loss. True, I've got more friction in the teeth because all that axial force is getting canceled by the teeth rubbing on one another, so that's not a total saving. I'm going to have perhaps some more friction than I had before. But these are used in a lot of applications where both high power, high torque, and quietness are valued, which would be any Navy ship you ever saw, especially submarines. And I've actually worked, and when I was just a pup, right out of high school, worked for a GE that made these things. And I remember walking through the shop, and there was a guy sitting up in a little tower, and the gear was as big around as this room is high, with no exaggeration. And he's up there watching the thing cut its way through to making these herringbone gears. It took about several weeks to go around the whole gear. So, cost no object there. So we got two opposite hand helicals. I've said this already, as you can imagine, expensive to make. The cheaper ones are made by literally putting two helicals together on the same piece by cutting a groove down the middle. So if I put that in a lathe and took a groove out of there, then when I'm cutting the teeth, I do that before I cut the teeth, my cutter then runs out into the groove rather than have to take the cutter and turn a corner in there. If the tooth's big enough, I can turn the corner with the cutter, and that's what they were doing with this battleship gear that I saw being cut back literally 60 years ago. 1956. How many years ago is that? 55 years ago, 1956. Worm and wheel we've already talked about a little bit. It's a single tooth or a thread. I already said all of this, I think. Non-intersecting axes also, and they're orthogonal to one another, which can be a help in packaging. Oh, I didn't mention single or double enveloping. What's meant by that is, imagine that you make the worm look like an hourglass instead of just a cylinder. And the teeth get bigger toward the end of the worm. It wraps itself around the wheel, so I get more engagement. Thus I can transmit more force, bigger teeth too. That'd be single enveloping if I let the worm climb up around the gear by making it hourglass shaped. And the other way is to take the gear, the worm wheel, and wrap it around the worm by making it wider and letting those teeth come down and wrap around the worm a little bit. That's a double enveloping. Now I can transmit lots of torque with that because I got a lot of surface area and a lot of cross-sectional area to take the load. And of course my friction goes up in the process. I've mentioned the back driving issue. I mentioned the efficiency being not so hot. And I can get big ratios in a single stage because I got one tooth on one gear. That's quite handy. And lots of torque. These are heavy-duty kinds of things. Dump trucks, big, heavy dump trucks have worm drives in the rear end instead of the kind you have in your car or your light truck because they're able to take that load that the truck is subjected to.
Is it
Oh, it doesn't affect the ratio at all. It's just your power consumption. So you're gonna warm things up instead of if you put 100 horsepower through and you're 50% efficient, you're getting 50 horsepower out and you're heating the atmosphere to the tune of 50 horsepower.
so can you
I don't think I need to because the ratio is locked into the kinematics. If I have effectively one tooth on the worm, which is typical, and I have 20 teeth on the worm wheel, sometimes called the worm gear, I got a 20-to-1 reduction. If I have to make 20 revolutions of the worm to make that worm gear go around once. Now that's true whether I have good efficiency or bad efficiency, right? That's independent of that. That's just the kinematics. But if I got crummy efficiency, I'm going to have to turn a lot harder on that worm to turn the same load that's on the worm gear, right? So I've got some load on the worm gear that has to be delivered, the torque that I'm delivering to the load. And if I'm 100% efficient, I can just put 1/20th of that in up here, right? 20-to-1. If I'm 50% efficient, I got to put in another half up here to make up for the losses because that stuff is leaking out the sides. Essentially, I'm putting that energy out the side of the gearbox as heat. And I got to put it in there, but not all of it comes out on the shaft, right? That make sense? The rack and pinion is another common application, and the rack is nothing but a gear that has been made to be infinitely large in diameter or radius. Thus it becomes a straight line. And if you want to generate an involute on the rack, then I have to send you out to infinity with the string and the piece of Scotch tape to stick it on there so I can put the pencil at this end and lift it up, right? So it's coming off a straight line, and I get a straight line. So the trapezoidal tooth that results from my involute generation on a flat gear or rack is a pure trapezoid. And this is very handy because that's easy to make. So I can make that thing accurately in steel, tool steel, harden it, sharpen the edges, and use it to cut my other teeth on the round gears, can't I? So this is called a gear shaper. So I put that in a machine that drives that tooth in and out of my picture up there. Drives the rack, I should say, in and out of the picture. And I put my piece of steel that I want to make round teeth on a round piece on there, and I cause that to increment slightly. and I go through there and carve it out. And in the process, I get nice-looking teeth which have a true involute because I'm generating them with an involute, which now you can see why if I have an interference problem, I'm just going to remove the material in the process of making the tooth, right? Because this is a true involute all the way to the tip. That's going to go in there and eat out the root if my pinion's too small for the size of the teeth and so forth. So I'll never see the material that would interfere on a physical gear because I took it out when I cut it. And I can use either spur, helical, or herringbone types of gear shapes on this thing. I mentioned the trapezoidal teeth. Commonly used in automobiles and rack and pinion steering. You've all heard that term. The pinion's on the end of your steering column, literally. So you're turning that with your hand. And disengage with a rack, and the rack is caused to slide in guides left and right across the front of the car. And the other end of the rack on either side is coupled to 4-bar linkages that go to the wheels and cause them to turn as you slide the rack left to right. Very direct steering. Its big advantage and why it's desirable, particularly in sports cars, is it's very directly connected. The option is to use a worm and wheel. Most other cars, if they don't have rack and pinion, they've got a worm at the end of the steering column and a worm wheel in contact with that, and that's turning a lever, which is the input to your links to go over to the wheels and turn them. And since worm and wheels have a lot of backlash, those cars may have a little bit of this in the wheel and not be tight. Whereas the rack and pinion, if it's done properly with very little clearance in here, can have very, very tight steering. And I already mentioned to use as a cutter. Bevel gears, rolling cones. The cones must intersect, so the axes have to intersect. But I can turn any corner. These are shown at 90 degrees, but I can have any angle I want. They don't pass power very well because you can picture that you don't have a lot of tooth contact there because of the funny geometry. So I don't have the same kind of wrapping that I get in a helical or a worm and wheel, where I get a real, good grip between the two sets of teeth. The line contact spiral simply puts the helical shape on the teeth and also will make it run quieter. And finally, hypoid gears. By the way, all of these gears are based on the family of conic sections, right? Cylinders, cones. And if I take a hyperbola, which is one of the members of the family, the guy that goes off to infinity, right? And I take that hyperbola, and imagine you're in a CAD system, you draw a hyperbola, and you rotate it about an axis, and you develop a solid. So now I've got something that looks like a crazy cone-shaped thing. It's not a cone, it's a hyperboloid. Continuous curve on the surface and growing bigger like a cone. And I can run two of those together. I can run any conic sections together, any like conic sections. And for them to nestle together, they have to be at some funny angle, like you see there. And the advantage of these is I have non-intersecting axes, which is not true of the spiral bevel or the bevel. I have to have the axes intersect, right? And in this case, it happens the axes don't intersect. They can be at any angle. This is shown at 90 degrees. That's shown as a general case. This is used in the rear end of most rear-drive automobiles and light trucks. And the reason it was used after World War II was because the call was for longer, lower, wider cars. The ones before World War II were tall. And the drive shaft running from the engine to the rear wheels was going through the middle of the passenger compartment. If you lowered the car down toward the ground, you had a big hump. And they wanted to get rid of the hump. So by changing from a spiral bevel in the rear end, they dropped the drive shaft down substantially, reduced the hump, lower car, harder to make, expensive to make because it's crazy geometry. But you pick up some other pluses. There's always pluses and minuses. There's always trade-offs. You make one thing worse, something could get better. This is bigger. This pinion is bigger than it would be for the same ratio up on the center line as a bevel. So I can make the whole thing smaller and still pass the same amount of torque. Smaller, lighter, cheaper. Probably not as cheap as the original spiral bevel. And I have the additional advantage of the offset input shaft, so I have a lower profile. And I know for a fact that some of the light trucks, like, half-ton pickup trucks, have these in them too. Probably because they're making so many of them, it's cheaper to use that in the truck. You don't care about the hump in the back seat of a truck, It's sort of irrelevant. So even in trucks, they are sometimes used, not on very big trucks, but I've seen them in some smaller trucks. So these are very common, automotive differentials. I'm just at the right time. I made it through. Tomorrow we'll talk about stresses in gears, so you can start designing your gear set so it doesn't break. You've already done the kinematics, I'm sure. You know what ratio you want. It's about, what, 6 to 1-ish, probably, for most of you, right? Oh, by the way, rule of thumb is gear sets are, it's recommended you have no more than a 10 to 1 ratio between them. This is not worms, but regular 2-round gears. Only because the minimum number of teeth is, what do we say, 16? That's 160 teeth to get 10 to 1. It's not to get big. So your packaging goes in the wrong direction. So to get the packaging better, you compound it. So you take 2 trains and multiply them together just to get the package smaller. So it's not a hard and fast rule, but rule of thumb, roughly 10 to 1 is a good limit for upper ratio. Your 6 to 1, piece of cake, 1 stage will do it. Don't need to compound it. So all you need is 2 gears. Your choice as to what flavor.